you have already seen some glimpses of this equation in the other module that Debabrata is covering on optimal transport. Okay. So nevertheless, let me sort of remind you a little bit of that. So what you do is that you start with a U which is say C2 convex. I'm just introducing the operator, and then what you do is that you take the determinant of d square of U. And the Monge Ampere equation is about to prescribe the right hand side f in terms of x, maybe u, grad u, and so on. And there are two goals of these three lectures. So the goals would be the following. One is to solve a set of d square u equals to this f, which depends on this with boundary value in a convex domain omega, and this is the boundary value on the denominator. This is the Dirichlet solvability. Which is, so suppose I just take 0 boundary values, okay, and this is a uniformly convex domain, and I want to solve this problem, let of d square u square. So what I do is, so the solution would typically be, okay, so this is the case when otherwise you sort of prescribe the boundary values and then you have to solve this problem in a way so that inside you retain the convexity. So I would try to emphasize strongly on this word convexity. Okay. Prior to that, let us see why do I care so much about f, x, u, du, and so on. Okay. So one geometric motivation besides the fact that it comes from a variational problem that Debabrata mentioned. Okay. So one geometric motivation is the Gaussian curvature So now if I have a graph, say, okay, lying on a plane, okay, suppose I have a graph of a function at any point x, I have a representation at any point x here. I look at the function value, this is x comma ux, and what is the Gaussian curvature? You go to the principal coordinates, okay, that makes the tangent plane 0, and then you take the product of all the principal curvatures, right? And for any graph, the Gaussian curvature has the following expression. It is for a graph, it is det of d square u over 1 plus grad u square whole to the n plus 2 by 2. So this is the expression at any point of the Gaussian curvature. So let's try to get a feel of as to why this n plus 2 over 2 appears. Okay. So what I do is the following. So I take the gradient. I take the direction of the gradient. Take the direction of the gradient and make that one of your coordinate direction at a point that I'm interested in. So let's take x to be 0. Okay. I don't want to bother too much. And I assume that the grad of u equals to un of en. Okay. Un of en. So at the point un of 0. What are the other points? So what I have is that along this direction, the graph looks like this. And say I have a plane. And this is the direction En. And this is the graph. Okay. So now along the direction En, I can apply my one-dimensional geometry, whatever knowledge I have. It's a one-dimensional Gaussian curvature, one-dimensional principal curvature, so to speak. And what is that? That would be, so along the direction En, if I want to write this matrix, okay, along the direction En, it will be un over 1 plus unn over un 3 by 2. So this is from the one-dimensional geometry, right? And now what I do is that, say this is the point 0. Now what I do is that I cut this sort of by a plane along a certain cross section so that it hits this graph, okay? I cut this by a vertical plane. If I cut this by a vertical plane, I don't think I'm drawing enough that I would, if you will broaden this color at the moment. This is how it would be, right? Yeah, so this is how it would be when I cut it by a vertical plane like this. So, and what is the size of the maximum radius that you can inscribe in this direction? This would be like, suppose this direction is say EI, some other direction, this would be 1 over UII. Okay? And this is related to the Gaussian curvature, as in like it is the reciprocal of the this is related to the principal curvature, as in it is like the reciprocal of the principal curvature at the points of zero gradient. And now if I move this tangent plane so that I move to the principal direction, okay? So this then tilts to this, and this length would vary from this length by something because I am only tilting the tangent plane by a length which only differs from this length by a function of the gradient at this point. And by a very elementary coordinate geometry right now, planar geometry right now, this length to this length would just be, if this length is 1 over UII, this length would simply be 1 plus UN squared of UII. This is the tilting. So, which is when I move this tangent plane, this direction changes to the principal direction in this manner, and this radius changes to this radius in this manner. So along the other principal axis which is there, I see that the size of the largest circle that I can inscribe is this much. Okay? And therefore, the principal curvature at this point would simply be UII, and so therefore I can do it along every other point, and so therefore this would be U11 over 1 plus UN squared half dot this one. Okay, and U22 over 1 plus UN squared. So the number of times that you're taking half is n minus 1 by 2. This is 3 by 2. That makes it n plus 2 by 2, and this is that of d square u. Okay, so this is the prescribed Gaussian curvature problem. So therefore, what I want to do is that suppose I want to solve this prescribed Gaussian curvature problem where I prescribe it to be some f of x with boundary value 0. Then to solve the problem, if I take this on the other side, this is the expression of f of x u gradient. Okay, so this is one motivation. And now the second, so this would be one goal of the course is to solve det of d square equals to f. Okay, and the second goal of the course, which is really the hard part of this course, is interior regularity of solutions. So the second goal of the course will be interior regularity of solutions.
So once we get the formula for the Gaussian curvature, how is that? What's the exact problem related to the Monge Ampere?
Oh, so the thing is that if I want to solve the prescribed Gaussian curvature problem, which is to say that at every point I prescribe this curvature and I want to solve for a graph which attains this curvature. But then in order to solve this equation, okay, you would need estimates that I will now come to at a certain point, okay, maybe if not at this talk, maybe in the subsequent talk. And then in order to sort of analyze the regularity of the problem, you have to put it on the other side. When you put it on the other side, it has essentially the structure of that. Okay. So I have to study interior regularity of the solution. So this is quote unquote in the sense that unlike whatever equations that we have studied, interior regularity just per se does not exist. Okay, for this problem, because this problem has, or the solutions to these problems have much higher degrees of freedom, as we will see, than its linear counterpart, which is the Laplace equation. And when you have a graph or a function or a solution which has different more degrees of freedom, it means that you can sort of do a lot of things to distort the graph in many other ways. Okay, but retaining the character of this equation. This is all words. Okay, so let me not emphasize even further. Okay, so and now the first thing that I want to clarify is that why U convex. Some of you already know why U convex. So what is the typical thing that you do in what did I say? When you have f of d square u equals to 0, you derivate it by using the translation invariance, you derivate it in a certain direction, okay? And then what you have is that del f by del ij d square u of ue ij equals to 0. So therefore, to run any sort of a good theory, we require this to be uniformly elliptic, right? I mean, if you don't require it to be uniformly elliptic, then you go into the realms of some other theory which is outside the scope of this symposium, so that I would not even try to allude to. But essentially, to have a meaningful, reasonable theory, we need some uniformity. Okay. So now the thing is that the Monge Ampere is slightly more structurally involved than a fully nonlinear equation which is uniformly elliptic. So let's try to do the same for this. So what that gives you is that, so suppose I have that of y equals to f. So for the time being, let's just assume f of x, okay? Then what I do is that I derivate this equation in some direction, okay? So now for that, just recall the rule of differentiation. So if I have that of x, okay, and I want to differentiate d by d epsilon at say epsilon equals to 0 in the direction b, what do I have? So this is equal to d by d epsilon at epsilon equals to 0 of that of, and I'm sure that Devu Prasad, I don't remember have done it already, but let me still do it, okay? I can't remember. And then you split the determinant. So you move this out, that of a, and then d by d epsilon at epsilon equals to 0 of that of, and then a inverse b. So any linear perturbation of the identity is only felt along the diagonal, right? And then all other places, at least it will be of the order epsilon square and so on, okay? So that is the heuristic. So therefore, whatever I pick up would only be along the trace, right? So therefore, this is equal to at epsilon equals to 0. This would simply be that of a times trace of a square b, a inverse b. So now with this, if I want to apply it to this chain rule, so I derivated differentiating. So differentiating one with respect to some e, with respect to e, a unit direction in Sn minus 1, what I get is that this would be equal to, so I derivate this, so this gives me that of, this will be, gives me that of d square u, trace of d square u inverse, and then I have to apply the chain rule to b, and that would simply be d square ue equals to f of e, right? Clear? And what is d square of u? That of d square u, f, right? So this is f. Therefore, I get the trace of d square u inverse of d square ue. So it is a linearized one, like the one over here, except that now you have fe by f. So for this to be uniformly elliptic, I need that d square of u minus is positive. So this is 2 is uniformly elliptic. D square u minus, d square u minus is bounded from below and from above by positive constants, right? And that is essentially the bound on d square u from above and below. So to have any meaningful theory, you require u to be convex. And now, suppose I give you, say, any ball, right? So this comes from a quadratic function, it's like 1 by 2 mod x square, right? Or from below, this is the 0 level, doesn't matter. Now you see that here all the curvatures are kind of the same, right? So the that of d square u, so for this, that of d square u is like 1, right? But now I have, what I can do is that I can stretch some directions. To this example, I can stretch this direction and I can squeeze in this direction. So this would give me a small curvature along this direction. And this will give me a very large curvature phi along this direction because I have very small time to go down and go up, right? So this will be large curvature, this will be small curvatures, right? But I can still maintain that the product be balanced. So what I can do is that I can have several perturbations of this, which is I can take something like delta of x1 square plus 1 by delta of x2 square, and I can still retain the structure of this equation. Okay, so therefore you see that this is an affine transformation which doesn't change the structure, and so therefore this is one aspect that makes Monge Ampere different from even its linearized equation, which is a linearization, which is a Laplace operator. The Monge Ampere operator has larger invariances, and in particular this affine invariance, and that makes analyzing the interior regularity of the Monge Ampere significantly harder than any of the elliptic PDs, including the fully nonlinear PDs that we have seen so far. So if you see the historical development of the subject, first Caffarelli understood the regularity for viscosity solutions of fully nonlinear equations around 89. Prior to that was the question of classical solvability, which was addressed, but that is where the regularity is inherited from the boundary conditions. But if I just give you a viscosity solution under geometric assumptions to have the interior regularity going, that is a significantly different theory. And that came much later in 91. Okay. So this is how the historical progression of the subject has been, and Luis Caffarelli has kind of spearheaded this entire theory. Okay. And then finally also consolidating some of his works and later being able to apply it successfully in the context of Monge Ampere, in the context of optimal transport that Debabrata would mention. But again, optimal transport has different difficulties because there the sort of this Monge Ampere measure, as Debabrata said, can be supported in a region which is outside the target. And so therefore he requires these additional global assumptions that he would talk about. So I'll come back, I'll also come to that. So now let me try to at least formalize this part rather than get distracted. So this is the affine invariance property. This is very specific to the Monge Ampere equation. So I'll continue over here. So what I do is that I take a transformation A, okay? So then what I do is that I define U tilde A be a linear map. I define U tilde of X to be U of A of X. And then what I see is that d square of U tilde, you can see after computation, is either A transpose A or A transpose d square of U of AX. So then when I take that of d square of U tilde, this becomes this determinant square, determinant of A and A transpose are the same square. So this is determinant of A square multiplied with that of d square of U and evaluated at AX. So suppose I start with that of d square U. So and this is equal to f of AX, right? So now you see what exactly I need to do. I need to multiply with a factor this U tilde so that this matches. And if I multiply, so suppose I multiply U tilde with a k of, so if I take U tilde to be k of U tilde, what is the factor that I need to multiply with? Because when I take the det of U tilde tilde, d square of U tilde tilde, this will be kn times det of U square U tilde, d square U tilde, which is equal to kn times det of A square times f of Ax. Okay. I mean, you may need to rename these variables, but let it be what it is. Okay. Since we are just doing it, and let us keep going. So you want to keep the structure as it is, f as it is, but not disturb the right hand side more. So the k that you need to multiply with so that it matches is kn equals to minus det A square or det A minus 2. So maybe on this part, I require kn times det of A square, right? Or k is equal to det of A minus 2 by n, right? So therefore, the right U tilde that I should have taken is, so if you forget about this U tilde and call it your new U tilde, so what you see is that if you solve det of d square U equals to f, and if you take U tilde, which is equal to det of A minus 2 by n U of A, then det of d square U tilde is equal to f of Ax. And this is the difficulty that I am talking about. Okay. So in a more simplified form in 2 dimensions, this is what it is, right? If I just give you a bound on the boundary, so what happens for Laplacian in U? If you have Laplacian equals to f, U equals to 0 on the boundary, okay, then you have some sort of a maximum principle, then you have that d square U or U infinity or U for any ck alpha is controlled by f, right? Far away from the boundary in the inside. But that doesn't happen for the Monge Ampere. Because if I look at this and I subtract of 1, then I can make this value 0 on the boundary of the ellipse, but then the curvature inside are highly distorted. So I cannot get a universal estimate even with the same right-hand side, because I can stretch some directions, squeeze some directions, or said differently, increase some curvatures and decrease some curvatures, but keep the product 1. So this kind of suggests that there could be a bunch of infinity curvatures and bunch of 0 curvatures, which still balances to be 1, right? So this is the real regularity issue, which is the interior regularity, which is why I said quote unquote. So this interior regularity is in general not true, and I will tell you, okay, in a while. So what is the other thing that I have to say before I dive into that aspect? So let me just think of it a little bit more. So this is one motivation, and for some of you who has not attended Devabrata's lecture, are there any who was not in Devabrata's yesterday's lecture? Okay, so let me just tell him very, very short, okay? Because I do see some faces, because yesterday I was looking through. Now, before that, let me make a very soft remark. Let me make a very, very soft remark, okay? So I take U convex, and this is an important remark. Because historically it is important. Even though this conference is about Luis Caffarelli, so I think historical omissions is not acceptable. So U convex, okay, and C2, and such that set of D square U square, where F is bounded from below and above, okay. So where F is like comparable to 1 and smooth, okay. Now the general strategy that people employ in this theory is that the general strategy is to bound D square U from above. You don't even need to put the sign because you will assume to be convex from C. And this will tell you what, that the eigenvalues are bounded from above. But this will also then give you an eigenvalue bound from below, because the product of these eigenvalues has to be 1 or comparable to 1. So this would imply that D square U is also bounded from below by C inverse. And now you come into, so you have a structure of uniform ellipticity. But that I said, if you just have uniform ellipticity, of set of D square U as there is, that is only good enough to guarantee you C1 alpha regularity. Because if I give you any fully nonlinear equation, it is no better than C1 alpha, right? The a priori estimates are no better than C1 alpha. It is only in case of concavity and convexity, if this operator has this additional structure, then you gain C2 alpha or C2. Once you have C2, then you can go all the way up to C infinity, because C2, because the nonlinearity depends on the Hessian. That is the principal difference, as I said, with the divergence form case. When you have a quasi-linear structure in the DiGiorgi-Nashmother theory, to get the solution to the Hilbert-Langdon problem, you just need to cross the threshold of C1 alpha. Then you can bootstrap because the nonlinearity is in the gradient. But since here the nonlinearity is in the Hessian, and in general you cannot do any better. And I said that there are examples due to Nadirash, Pili, and Breton. So at this point, I would just have that with C1 alpha. But then this Monge Ampere operators, if you perturb it a bit, okay, if you write it differently, is also a concave operator. So that is what I will say now. So any more regularity by Ivan Sprilov, should not spend too much time, because this is just a general strategy for the next 2 lectures, okay? And some preparatory tools has to be covered. But Ivan Sprilov tells you that we need concave convex structure, okay? So I will first tell what is the modern approach to such problems, and then tell you some historical results in this direction, where at the time when the Ivan Sprilov theory was not known. Okay, but that will be later. But this is also important for my later work. So what I know is that, so given any A, say assume to be positive, okay, what I can do is that I can write, well, let me write B. Set of B whole to the 1 over n can be characterized as infimum over all A positive, set of A equals to 1 of 1 over n of a trace of AB. So that means that the determinant raised to 1 over n is the infimum of a family of linear operators. So it is a concave operator. Right? So the Monge Ampere operator is an extremal operator. It is the envelope of a family of linear operators. So that imparts it a non-divergent structure. But Monge Ampere is one such operator which lies at the crossroad of divergence and non-divergence PDs. It is, of course, having the divergent structure because it comes from a variational optimal transport problem. But even otherwise, what you see is that if I have det of d square u over a set S, this is essentially the measure of grad u of S, right? So det of d square u is the volume of something, and hence it is equal to the divergence of something. Okay, so that is another way to see. Anyhow, so do you require a proof of the step? So this just follows from the trace determinant inequality. So that says that if I take det of A, det of B, less than equal to trace AB over n. I just wanted to show you because it is not just the there is a special A that realizes it, this infimum n, right? So then the thing is that I want to move 1 by n, okay? So I move this and I move everything to be 1 by n. So I take 1 by n, I take 1 by n, right? And now det of A is equal to 1, which I happily ignored. So at least you see the bound from below. And now what I do is that I apply to the special A, which corresponds to the cofactor matrix of B. I mean, I don't know whether it's cofactor or minor, but I will tell you it is essentially det of B times B inverse. Okay. So now if you take A to B, det of B times B inverse, then you get that det of A is of course equal to 1, and trace of this A, trace of AB will be equal to det of B times trace of B inverse, and that has to be n, right? This is identity, this is n, and there is the n that is below that cancels, so this realizes it. So the determinant is not a concave operator, but a power of determinant is. The correct power of the determinant is a concave operator. Okay? So therefore, you have the concavity. So as soon as you get a bound on the d square u from above, you get a bound on the d square u from below, you realize that a change of this operator by this det to the 1 by n is a concave operator, and therefore when you put all this information into your problem, and at this point you are able to set up the state where the classical Evans-Krylov theory can be applied. You get C2 alpha, and then you can get all the way up to C infinity. Okay, so as long as you can prove an estimate on the d square u from above, you can improve the regularity in a local as well as a global situation, depending on the right hand side and the boundary. Clear?
That's an inequality on the right, right? So how do you get equality there?
Apply it on the special A.
And this is an inequality, right?
Yes.
Not an equality.
Yes, but that is fine. So that shows that, okay, so at least it is there. So it is always less.
Okay.
So for anything, it's always less than det p to the 1 by n.
Yes.
Now I want to take a special A which realizes it.
Okay.
And that special A is this. The one over here. And I know B of B inverse is a very nice matrix, it's an identity matrix. So trace of identity then n by n is 1. So this has determinant 1. Okay, and I take B to be positive, so this is also positive. If B is positive, B inverse is also positive. And then I just apply, so that of A, so trace of AB.
You know what I'm saying? Why is there equality there?
Oh, because I'm able to find the A which realizes this. If I take A to be this, this value is exactly that B1 by n. Right?
Okay.
Right. So okay. So in fact, what I should have done is that I shouldn't be taking this. I should be taking 1 by n. Now is it clear? I made a mistake. You take det b to the 1 by n. Now whatever comes out is exactly det b. Well, det b to the 1 over, yeah, I think it's fine. Right, because in determinant, at any given point of time, only n terms multiply. So you had the right objection. Okay, so it's good to sort of correct this. Okay, so don't take that b to the 1 by n. Okay, so this is 1, and now you see that, but so this is one such concave sort of a modification of debt. There is another concave modification of debt, which is very important for some very serious estimates concerning Monge Ampere, which I will refer to as the Kokolorov estimate, which is one of the most significant estimates for the Monge Ampere that Luis Caffarelli has to use at several places. So that I will come to later. But first, once I know that debt of B1 by n is concave, so therefore I see that for debt 1 by n is concave. I compose a concave with a concave, it's still concave. So this will tell me that the log of debt 1 over n is concave in the cone of positivity matrices, in the cone of positive definite matrices. So this goes like 1 by n. So I ignore this 1 by n. So I get that log of debt is concave. But in my last, before I reach my last lecture, I need to get a hold on this quantitative concavity. Okay, that will be again important for this estimate of Kokolorov that I was mentioning. But let me keep going. Okay, so this is one thing. So you see that this is how roughly the theory is, and the other more modern motivation has come from the optimal transport problem. And okay, so prior to that, I should also say that I should also remark that okay, so the modern approach to this problem would be you get a bound on this Hessian from one side, you get it from the other side. It falls into the classical regime because certain modification of this debt operator is a concave operator to which the Evans theory applies, and you can get interior and boundary regularity depending on what the right hand side and the boundary assumptions are. But the classical approach to this has been, so once you know that B square U is bounded from above, it's also bounded from below, is due to Calabi, got a third derivative estimate. And there, from there you can apply Schroeder, and then if you combine Calabi with Schroeder, you get C infinity, depending on what the source is and the boundary is. And so this Calabi's estimate exploits the special structure of the Monge Ampere in a very, very clever way. Okay. So there has been a historically, once you get a bound on D square U from above, because of thanks to the special structure of the Monge Ampere, there is this Calabi and also Kokolorov's estimate that allows you to get C3, but I think it's primarily Calabi. So historically, you will combine Calabi with Schroeder. In the modern theory, once you have a bound on D square U from above, you will combine Evans-Krylov and Schroeder. Okay, so this is the perspective to be noticed in this regard. Okay, so now the other modern application, so to speak, modern because it has only surfaced maybe not more than 35 years ago, is the optimal transport. Okay, application to optimal transport. I really don't want to waste time because Kokolorov is already covering it. So you have this mass to be transported here. Okay, this has the density mu, which is f dx. This has mu, which is d dy, which is rotation, and you want to transport it by t, which is measure preserving. P at mu equals to mu, which is to say that for any b, I take the inverse image, okay, which is t inverse of b, and I map, and I want that mu of t inverse b equals to rho p. Right? So, and then you want to minimize this variational problem. So the cost is say the distance square, okay, as we mentioned, x minus dx squared of f of x dx. So, okay, in x. So this is x, this is y. And then he mentioned about the theorem of Banerjee. And then in 1987 or 87, please. Banerjee showed that for this quadratic cost and later on for mode mentality, strictly convex cost and so on and so forth, this T can be realized as the subdifferential of a convex function U. Okay, I'll come to this. I think I should have mentioned subdifferential before to make sense of a meaningful weak sense of the solution, but since I'm into it, let me continue. Okay, so it's like this. So this has to be interpreted in the right sense. The subdifferential, which Kokolorov has already mentioned. So for most of you, you're not finding this an alien kind of symbol. Probably he's also used LU, so these are kind of like depending on what you're comfortable with. So what happens? So if I have something like here, I have a small region which I call it f of x dx that gets transported to. So this region here gets transmitted to t of x dy, and this dy gets magnified by the change of variable, which is equal to it gets magnified by det of this d square u, right? Det of t. So det of dt is det of d square u, because this region by this t, okay, the volume factor is det of dt, which is det of. So it becomes g of grad u, g of tx. Let me first write it as det of jt. Okay. Here, this is the magnification, right, of this factor, and this is exactly gy dy. So this region is gy dy. So now I'm using certain properties of this differential. That the thing is that the differential is essentially 1-to-1. Okay, at the points where so I will show. I'll show a few properties later. Okay, so the differential is essentially kind of invertible. Okay, at least the set of points where value of E intersection value of F for any two disjoint E and F is of -0. Okay, so anyhow, he has mentioned, Devabrata has mentioned all of that, but I'm just doing formally. Okay, just to see where this Monge Ampere appears. So now, when you sort of put this together, what you get is that f of x equals to g of grad u of x, det of jt, which is d square f u. So you see that for this, formally, this is equal to f of x divided by g of grad u of x. But again, this is to be understood in the linear way that Devabrata did, and this is different. This will be different from the weak solutions that we will introduce for the Monge Ampere. Okay, and in general, the global assumptions come into play, as Devabrata mentioned that if in general, this T can be highly discontinuous, even though it has this formal representation. Okay, but it is this formal representation around 1987 that pushed several people doing regularity theory into this, and primarily Luis Caffarelli. Okay, because around the time 87, 90, he was into fully nonlinear equations well, besides looking at various free boundary problems. Okay, when I don't even know how many days we require to summarize his largest contribution in free boundary problems. We could just do very little during the course of all these lectures. So anyhow, so in general, Devabrata mentioned that if I take this ball, I slide it here, take this half ball, right, 2 times, well, it looks more than 2 times. I think I've stretched it too much. And then you take this other piece. So the optimal map one has to show is exactly this, okay? And then he showed that, so this is a discontinuous map and it is expected, this optimal map is expected not to be continuous. Why? Because the image itself is a discontinuous set. Okay, so then you may straight away raise an objection that why do I care? Okay, but the thing is that he also told you about the stability of these optimal transport maps, okay, and which is a consequence of the cyclic monotonicity. He said that if you can control it by a little tunnel, very little tunnel, okay, and you need to round off these sort of these measures appropriately so that you don't change the mass, entire mass around, and if this epsilon is small, then along this slit it is discontinuous. Okay, because it turns out that the Banerjee measure, okay, det of d square u is supported in y. The Monge Ampere measure is supported in y. But the entire Monge Ampere measure that we will introduce not only contains this, but also contains this entire rectangle that he mentioned. Okay, so there is a slit which contributes a large chunk of this measure. Okay, so this which is not present in the target that it maps to. Okay, so and then Caffarelli showed that if this kind of situation is bypassed, that if you assume that the target has convexity, so what Caffarelli showed was the following. So then Caffarelli showed if y is convex, with good assumptions on the cost, good assumptions on the densities, okay, then U is a weak solution that I will introduce, which is referred to as the Alexandrov solution. And moreover, the key thing that allows you to rule out flat examples is that if you put a tangent plane, support plane, there exists a support plane on the graph so that the graph has to lift, okay, and strictly convex. Okay, and then in this situation, Caffarelli's Monge Ampere theory that I will describe applies. Theory applies. This is the wide significance of this Monge Ampere problems. Okay, there is another one, but prior to that, let me introduce now. This is just the right point to introduce, or maybe I should have introduced much earlier the weak solution. Okay, so in general, even if I give you Laplacian of U, okay, you cannot give me, if I give you a general smooth domain, you cannot give me a smooth solution right away, right? You first have to apply some L2 methods or some function space methods to get some solution, and then you use this equation to keep gaining regularity and see that the function actually belongs to the smaller space, okay, that you are interested in. So the bigger space is only a placeholder to begin with, so that you can guarantee the existence, say in h minus infinity, and then you come back to whatever h positive h that you need, okay? So this is a joke, okay? So don't take it seriously. So weak solution. So generally, you have to define what is a weak solution. So now let's try to understand the structure. So delta of v square u equals to f, right? So if I integrate this along with set e, I integrate this along with set e, and this by change of variable is that u, at least in the case when u is c2, is equal to f of e. So now you see, from this to this, I have lost one derivative. That is, to define this, I can always say delta of v square u equals to f if the image of the gradient map is equal to integral of f over e. But in general, a convex function can have corners, right? But what a convex function has is the subdifferential. The subdifferential set is non-empty. So this is something Debabrata has told repeatedly, and you all know. So given u convex, I can define the subdifferential of u at x to be the set of all. So now I'm changing notation. So I do not want to use two different notations. So grad u of x. So this would be different from the one that Debabrata introduced, which is the set of all p such that you set so the support plane lies below the graph. Okay. So this is the graph say. It could be a corner, and this is say the direction p. Okay, that you have. So this is the set of all p such that u of y is bigger than equal to u of x, the value at x, plus p of y minus x. And for a convex function, this set is non-empty, point by point. So what I do is that, so therefore, grad u of e is the union of grad u of x for all x in e. And therefore, with this, you can define this notion. Okay? So this happens for all e. All e Borel-Menger. Okay?
So in this case, the test functions are like test sets.
What?
Is the test functions are like the sets on which you can vary.
Okay, traditionally, if I know correctly, it has been done on continuous function. But I'm very sure that if you have a good Borel-Menger set, you can approximate that by a good continuous function, which is 1 here and becomes 0. And I can bet you on this that you can show that this would be equal to this. Okay? So this is not a major point. Okay? So I would not want to stress on this too much. So okay, in general, you have to define it by the continuous function, but you can at least cover the chunk of Borel-Menger set. Now the key thing to know is that, so therefore, this can be my definition. As Debabrata did, for a u, I will define the Monge Ampere. I mean, I find it difficult to write. Monge Ampere measure like f dx. Okay, this is how I will represent. And what this means is that when I integrate this, this is what I have. Okay, so in general, and the first thing that I need to show is, so therefore, so this simply means that this will be the representation that in the weak sense, delta of v square u equals to f is the corresponding Monge Ampere measure equals to f dx. Okay, clear? So this would be even more clearer in that case. So now the thing is that I have to show some basic properties, right? In the very first place, this is a legitimate measure. That is, so this is a lemma which I want to prove. It says that if I send E to the measure of del of E, this is a Borel measure. right? In any measure, we don't care about most of the other properties because they're ugly, but the main thing that we need to care about is that it is countably additive, which is to say that on disjoint sets, they can't have too large intersections, right? Because the outside is the Lebesgue measure. So now I want to say that that is, so therefore, the key thing to show is that, if I give E and F disjoint, then E F intersection phi, then grad U of E intersection grad U of F is of measure 0. And this is because this is also something Debabrata has already said. So what you do is that one way to see it is by the Legendre transform, it inverts the differential. Okay. So the Legendre transform U star of P is defined to be overall X in Rn. So it's a soup of affine functions. So it's a convex function. And the key thing is that P is in grad U of X. Only if X is in grad U of P. Okay. So therefore, what I want to say is that.
So if you started with the probability density function on F, isn't that by default will be a measure because you said these two are the same, right?
Yeah, but if I have to define this general weak notion, I need to make sense of the quantity on the left. But this quantity on the left in that case, so finally I would deal with delta of d square u equals to a Borel measure.
So we haven't proved that equality holds for
well, this is just the motivation that for a C2 function, if the C2 convex function, this has to match. But if this is meant to be my notion of a weak solution, then at least I do need to make sure that this, the left-hand side of the measure is a legitimate measure. And the key thing is that at least when I sum things up, the intersection should not have a large overlap. And so what this Legendre transform does is that it inverts the differential of the supporting plane, okay, the tangent to the supporting plane. And then you see that, I mean, have you seen this? You have shown it, right? He did show this. Clear to all? Or the, huh? Okay, so let me just, so this is the last thing I will show that even if he has shown, okay, because it seems like you don't see too much of not. But this is the bad part of not attending all the lectures. So U star of P, supreme of P dot X, so I have to show that. So what I do is that I take U star of Q. This by definition is bigger than equal to Q dot X minus U of X, and then you sort of match it by P. So if you write it as Q minus P X plus Q dot X minus U of X, but this is exactly equal to U star of P, right? Because P is the supporting plane. If P is the supporting plane, then U star of P is P dot X by this, right? Because any other point is like, right? This is clear? So this tells you what? That X is the supporting plane of U star at P.
X belongs to grad of U star.
Grad of U star. Sorry. Is it clear? I'm very sorry. So this is how it inverts. Okay. Otherwise, it makes no sense. Okay. Clear? So is this implication clear now? Because if P is the supporting plane, then this is the place where it is realized, because otherwise the graph has to stay up. Okay, and therefore this is just so therefore this is because P is in grad U of X. So this inverts. So therefore, so if P belongs to grad U of X intersection grad U of Y, okay, then X and Y belongs to grad U star of P. So, and the number of such, and U star is being a convex function is Lipschitz. So Rademacher's theorem tells me that there is a unique tangent plane at almost every point, modular set of measure 0, differentiable almost everywhere. So these would typically be, any such P will be a non-differentiable point of U star, and there cannot be too many. Okay, so that has measure 0. So this is roughly the teaching. So of course there are a lot of things to prove. So now the other properties that are important in the entire analysis, which I will not have time to prove. So if mu k if uk convex converges locally uniformly to u naught, then the Monge Ampere measure mu k converges V star to Monge Ampere of mu naught. And then is the comparison principle. Comparison. These proofs are hard, and I will show you some glimpse of the proof in a while, because when I do regularity, I would need all of those, but not at this moment. Okay, so this I will just roughly explain. So what you have is that if u is less than equal or u is bigger than equal to v on the boundary of omega, and if the Monge Ampere measure of u is less than equal to Monge Ampere measure of v, okay, inside, this is just telling you that v is more convex, u is less convex, right? So this is the picture, right? Monge Ampere measure means more, the Hessian is more, right? More positive. So here is say u less, this is more, okay? So this has to curve up from much below, right? To have more sort of Monge Ampere measure, right? Yeah. This has to be more convex, so more below. So this implies that vu is bigger than equal to v inside. Clear? Picture is clear, right? So this will have more data of d square u than this, and hence the more Monge Ampere measure in terms of the comparison. And now, so this is the perspective that Russian geometers introduced, and primarily Alexandrov, okay, in the 1940s. So you may think that why do I care about, because finally in the Monge Ampere problem, I only care about data of d square equals to f. Now, why do I care about a very bad Borel measure? Well, this is important because this is important from the point of view of existence, okay? So existence. So this in particular will give uniqueness, okay, and existence. The existence was done by Alexandrov in 1940, 41, whatever, by what is called polyhedral approximation. This is a key thing to it, because any Borel measure, so it's not just about the fact that we want to develop a very general theory, which might not be of interest to all because my starting point at least appeared more juicy. But even to solve this Monge Ampere problem in the very beginning, these Borel measures are important because I can approximate it by, in the weak star sense, I can approximate it by sum of Dirac measures. So I can write it as, so mu k converges weak star, that is, if you integrate a continuous function, that is weak star convergence to mu, and when mu k is simply summation ai li I equals to 1 to some m. And if you want to solve the problem, first you want to solve the problem data of d square of u in the Monge Ampere cell. So you want to solve mu of mu equals to mu, with u equals to 0 on the bound, right? In omega. So this is the Dirichlet problem. So what is it that you? If I just have, so this is another property that I will use now. So if I just have summation ai, now let me first give an example on how you sort of capture the. If you know that u is C2, then the Monge Ampere measure is simply data of d square u dx. But let me give you an example where non-trivial Monge Ampere measures appear. That also Deepak has done. So what you do is that just take R1, okay? You just take x plus x square. Sorry, mod x plus x square, okay? So therefore, what I have is that outside x is linear. So the Monge Ampere measure is simply, so when x is not equal to 0, x is linear, so the Monge Ampere measure is simply 2 dx. But at 0, so this is more like a curve. This is like x equals to mod x, and the function is kind of curving out in a way, and so that near 0, there are no other supporting planes except for the ones to mod x. Why? Because x squared increases at a much slower rate than any affine function that I take, any line that I take, which is more than the size of this unit interval. Because this entire unit interval, if I take mod x, is part of the support plane, right? And if I take anything which is like 1 plus epsilon times x on one side, it is going to cross this x square at some point very close. Okay, so that cannot be a supporting plane, right? Because x square is very less compared to x. So therefore, at 0, the Monge Ampere measure has what? So the Monge Ampere measure will have the entire thing minus 1 to 1. Okay, right? So this is part of del u of 0. So therefore, the general, in this case, if I call it u, the Monge Ampere measure mu will be equal to this length of this interval, which is 2 Dirac plus 2 dx. Correct, right? So this is the Monge Ampere measure. So these are non-trivial examples. So therefore, why do I want to do this? This at least would have already given you the idea. Because if I just have some A times del naught, at least you see that you can always build a polyhedral sort of a, you can build a cone, okay? So how do you solve this problem? You apply the Perron method. And the Perron method tells you that you take all sub-solutions U, you take all U such that U mu is bigger than, sub-solutions V such that mu V is, well, mu V is bigger than equal to the mu that I'm interested in. So mu that I'm interested in now is just the summation of AI del I equals to 1 to K. Okay? Because if I know how to solve this, then I can go back by stability and get the solution to the original problem. Okay? So of course, I mean, you have to establish basic estimates, but convexity tells you that the whole family has to be compact all the way up to the boundary, right? Because there are uniform ratios that convexity allows. So U mu is bigger than equal to this mu, and V is less than equal to 0 on the boundary. Okay? And then what you do in the Perron method, you take the soup of all subsolutions. So you expect that U naught being the soup of all subsolutions will be your solution. Of course, this requires some work to show, and I will just indicate a line or two. But prior to that, let's try to understand why this set is non-empty. Okay? That is the key thing, right? Before you can sort of set up the stage for anything else. So what you do is that in one dimension, you see that if you have some of these, you can always build up sort of these kind of lines, okay? So that at every point you take the mass which is decided by the AIs at that point. You can sort of create the mass in that manner, okay? But in other dimensions, what you can do is that for a given A naught, del naught, you can at least always find a cone, okay, which is below that, okay, where this mass is created. And that this can be done in every dimension. And now you use the property of the determinant that which follows from a Brun-Minkowski inequality, which is det of A plus B 1 over n. I mean, it's just A and GM, det of A 1 over n plus det of B 1 over n. If these are general sets, it's a Brun-Minkowski inequality. But of course, for a matrix, it's much easier. Okay, it's, because you know that if you have two positive semi-definite matrices, they are simultaneously diagonalizable, and then you have to do A and G in a clever way. I won't even try to do because I'm sure that I will mess up. Okay, the proof. So I quit on this. But if I raise it to power n, I would just use the fact I will raise this to power n, and this will be bigger than equal to det of A plus det of B. So I do it for each of these AIs, and then if I take, so for each UI, they correspond to AI del I at those del of xi at this point, and then if I take the summation of UI, so these are like the cones, right? So these are like the cones situated at xi, C of xi, which I call as Ci, these cones, right? So, and then when I take the sum of these cones, sum of these Cxi, because of this property, okay, and then what do you do for a general U? You regularize it, you mollify it, the convexity retains, and if you use this property, you will see that the Monge Ampere has this property that if you have this, so this will have the corresponding measures to be summation of Cxi, and this will be bigger than equal to summation of mu Cxi I equals to 1 to n. This is essentially this property of the determinant. If I n make it 1, then this is what happens. Okay, this sums up in this manner. Okay, good. So therefore, I know that this set is non-empty, and this has a limit, which is exactly that, which is the solution. And let me tell you, and solutions cannot be supported anywhere else, because then the problem is that for this finite Dirac method, the solution could be supported somewhere else, right? And I want to show that that cannot happen. So, and that is really the key thing to the proof of the Alexandrov result, because the other things are soft. Okay, so which is that if I have these are the 2 points x1, suppose I have just x1 in dimension 1 and x2, these are the points where I had the right Dirac masses, and then what I do is that I create this kind of a region. Okay, so I create this region x3. Suppose the mass comes at another x3. What I want to say is that this cannot happen, because if there is a mass, there is a plane so that this separates from these two values by delta, right? There is some delta that separates it. Then what I can do is that I can sort of move up by an ordered delta over here, translate this graph, and then cut it by this graph. It is still in that family, and it violates the maximality. And for the same reason, if the slope at this, so therefore there cannot be support at any other point. Roughly, this is roughly the theory. And if there is a support at a point, now I consider a single point, And if this at this point the support is the mass AI is more than the slope that I required. Suppose the slope that I required was actually something like this, and the mass that I get is more, then I also have a luxury. Then what I can do is that I can dilate the slope a bit and continue it. So whatever the slope is, I can dilate the slope a bit, multiply u by some 1 minus delta. So and then sort of add that delta and push it in this manner. So I can sort of, what I can do is that I can push it up because at other points they are far away, because they're discrete points far away from this, and there I can continue it by this slope. And this will again violate the maximality. So therefore, not only the limiting one is supported at this point, it has to have the same mass, because otherwise you feel like you can lower the slope so that it's bigger than, still bigger than this slope. Okay, and it goes up. So therefore, it's in the class of subsolutions where the mass is more than the supporting mass that I'm interested in, and therefore this is a strict violation. Okay, so this is how you get existence. Okay, existence of these solutions. And what else? So what can you say about the regularity? So okay, so I have built the theory, and now I care about strong F. Strong F means good F. Okay, so what is the time that I have? So it's already 10:02, so I will stop the lecture now, and this segment of this lecture would continue a bit in the next one and up to the final one where I have to get the full-fledged regularity. So bad end, but it is what it is. Okay.
What would be an optimal solution for a single delta?
Well, you can just go